Okay, so the next speaker is Josiah Oh at Fudan University, and he's going to tell us about quasi-isometric rigidity of high-dimensional graph manifolds. Please start.
Thank you. Yeah, thanks to the organizers for this conference and for the invitation to speak. Today I want to tell you about, it's mostly like an expositional talk, but if there's time, then I'll say a little bit about work that I'm trying to do to generalize the result I'm going to tell you about. So this is a GGT conference, as I understand, but let me not assume too much and start from some basics. I also want to warn you, I don't plan to actually give any precise definitions, maybe just main ideas. So if that bothers you, I apologize, but I think it'll be okay. So one of the major ideas in geometric group theory is to think of finitely generated groups as geometric objects. And the way that works is you fix a generating set, and then it induces a metric we call the word metric. Alternatively, you can think of what's called the Cayley graph. The vertices of the graph are going to be the elements of the group, and then there's some rule for deciding when two vertices are connected by an edge. But here's an example. And despite how this is drawn, so this is supposed to be the Cayley graph of the free group of rank 2. Despite the way it's drawn, all edges are supposed to have length 1. And maybe I'll also just quickly sketch the standard Cayley graph for z squared. Yeah, looks like the integer grid. Now, different generating sets induce different metrics. So the isometry type of a group is not well defined. But if you relax your notion of equivalence to that of a quasi-isometry, then what we get is something that is independent of the generating set. Now, like I said, I won't define what quasi-isometry is. Hopefully most people here already know the definition. And if not, then let me just say that, well, it's like an isometry, except you allow for some bounded error. And the idea is, okay, these quasi-isometries, they may not even be continuous, so there's no reason to expect these kind of maps to preserve any of the local geometry of the spaces. But since the error is bounded, it's controlled. The point is that these maps still preserve large-scale geometry or coarse geometry. Yeah, so let me get to talking about QI rigidity, quasi-isometric rigidity. And the place to start is Goromov's famous theorem on groups of polynomial growth. So this is the statement of the theorem. A group has polynomial growth if and only if it is virtually nilpotent. Polynomial growth, yeah, so the growth rate of a group is just going to be defined as follows. You look at the ball of radius n in the Cayley graph. So for example, fix the identity and then look at ball of radius n and then count how many elements are inside that ball. And then the volume of that ball is going to grow as n grows, and then the growth rate of the volume of the ball as your radius goes to infinity is defined to be the growth rate of the group. This is invariant under quasi-isometry. So if you have two groups or two groups that are quasi-isometric, then they'll have the same growth rate. And then Gromov's theorem is basically characterizing groups that have growth rate a polynomial function. Okay, and then maybe I should also say something about this word virtually here. So a group is virtually some property if it has a finite index subgroup with that property. So here virtually nilpotent just means that the group has a subgroup, finite index subgroup that is nilpotent. So yeah, and then this was a very celebrated theorem, and around this time, Gromov proposed like a large program or direction of research, which is to study finitely generated groups up to quasi-isometry. And This is not like something that like we as people hope to eventually finish. It's just it's not feasible to expect that we can one day actually classify all these groups, but it's a motivation for a direction of research that's still very much alive today. So in this program, there's, even within this one direction of research, there's many branches that one can go down on. For example, something that many people are interested in is identifying QI invariance, quasi-isometry invariance. For example, I just told you that growth rate is invariant under quasi-isometry. Another kind of large subsection of this program is called quasi-isometric rigidity. And now, depending on what you're reading, QI rigidity sometimes has a more precise definition, but I think the idea that I just want to tell you today is that QI rigidity is just the phenomenon that occurs when the geometry of a group tells you something about its algebra. So for example, Gromov's theorem on groups of polynomial growth can be phrased as a QI rigidity theorem, because it's saying that the geometric properties of the group, namely its polynomial growth, is telling you something about its algebra, namely that it's almost nilpotent. Let me also say something more about this word virtually here. You might ask, can this statement be improved? Can you say that polynomial growth implies actually nilpotent on the nose? And the answer is, in general, you're not going to be able to do that because, like I was saying before, quasi-isometries only preserve structure on a large scale. And in terms of groups, what this means is that quasi-isometries don't distinguish between things that differ by finite groups. So another way of saying that is that if you have a finitely generated group, it's always going to be quasi-isometric to any of its finite index subgroups. It's going to be quasi-isometric to any of its finite extensions. So quasi-isometries are not going to let you detect differences by finite groups. So all these theorems, well, the theorems I'm going to show you today, at least, you're going to see a lot of places where we allow for finite error. And that's just how the theorems usually go. Okay, so there have been lots of classes of groups that have been shown to be QI rigid or not. And I could spend a lot of time talking about that, but since time is short, I just want to tell you about the class of groups that I'm going to focus on in this talk. And those are the fundamental groups of so-called high-dimensional graph manifolds. So these manifolds are a class of spaces defined by Frigerio-Lafont-Sisto. Again, I won't write down the precise definition. It would be way too long. Let me try to instead tell you the idea. So high dimensional is just to say that the dimension of these manifolds is always at least 3. And then graph manifolds, you'll see why it's called that in a second. So let me tell you what these things kind of are. So fix a dimension n, say it's at least 3. Now take a hyperbolic finite volume non-compact manifold of dimension at least 3. So maybe it'll look something like this. Since it's finite volume but non-compact, it's going to have some cusps. Oh, that takes a while. Okay. Now these cusps are going to be diffeomorphic to a torus times an interval. So what you can do is you can truncate the cusp, you can cut it off, you can remove it's called a horospherical neighborhood of it. And what we're left with is something like this here on the left. This is now a compact manifold with boundary, and the boundary is here a torus. So suppose this has dimension n1. Oops, sorry. And then what we're going to do with this thing here is we're going to take the product with a torus of dimension n minus n1, so that we get a n-dimensional manifold. Since this boundary component is a torus and we're taking a product with a torus, what we get is a compact manifold, again with boundary being a torus. We do the same thing with any number of finite other pieces. So here, if this thing has dimension n2, then we take the product of this thing with a torus of dimension n minus n2, and so on and so forth. So in the end, we get some finite number of pieces, all of which are dimension n, and the boundary components are all tori. Since the boundary components are all tori, we can fix some pairing of these boundary components and glue things together. For example, so we can do a gluing here, we can do a gluing here, we can even do a gluing like this. And now I don't make any, well, at least in this talk, I won't make any restrictions on how the gluing is done. But you'll notice in particular, like so here is it's an n minus 1 dimensional torus, and same over here, this times this. And when you do the gluing together, you can do a twist so that like the fibers don't necessarily get mapped to the fibers, but instead you have fibers go to the base, and then on this side the base goes to the fiber. But anyway, so that's the rough idea. A manifold is called a high-dimensional graph manifold if it emits a decomposition like this. And why is it called a graph manifold is because the fundamental group of such a thing is going to be isomorphic to the fundamental group of a graph of groups. I won't define what that is, but as the name suggests, there's some underlying graph, and I hope you can see the parallel between this picture here and the picture here. In a graph of groups, you have vertex groups, so you associate to each of these vertices a group, and you associate a group to each of the edges as well. And yeah, I hope it's clear the underlying graph structure here of this graph manifold. So this is the object. This is the object that these three people studied. And they proved a bunch of rigidity results about these spaces. And the thing I want to tell you about is their theorem about the QI rigidity of these things. So let me show you the theorem. So let M be, they impose an extra hypothesis, which I'm probably not going to have time to talk about, but an irreducible graph manifold of dimension n obtained by gluing these pieces. So Ni is going to be that finite volume non-compact manifold, and then the bar is just going to be indicating the thing you get, the compact thing you get after you truncate the cusp. So let M be this graph manifold, and then let gamma be any group quasi-isometric to the fundamental group. So here, I mean, the fundamental group of M, pi1 of M, it's a finitely generated group. It has some structure, and here we're letting gamma be any arbitrary group, and we're only assuming information about its large scale geometry, namely that has the same large scale geometry as the fundamental group of M. And the conclusion of the theorem is that this information alone lets us determine the algebraic structure of the group. So gamma is virtually, here you see virtually again, so passed to some finite index subgroup, and you get something that's isomorphic to the fundamental group of a graph of groups satisfying the following conditions. The edge groups are virtually free abelian group of rank n minus 1, and then the vertex groups are quasi-isometric to the fundamental group of some piece. And the point is, the way you should be reading this theorem is that all we're assuming is that a group is quasi-isometric to pi1 of m. Pi1 of m we know admits, or it is the fundamental group of a graph of groups. And the point is that gamma then is forced to be also the fundamental group of a graph of groups, very much like pi1 of m. Okay, there's this last piece here. You might complain and say, this isn't really describing all of the algebra. And so that's why there's this next theorem, that when you have groups that are quasi-isometric to these kind of things, there is also rigidity there. So they prove the following statement. So let gamma be a group that's quasi-isometric to the fundamental group of some piece. And then the point again is to say that the group algebraically is like that piece. So it's a lot of words and a lot of symbols. And if you have the time, you could certainly parse it and make sense of it. Let me try to just do that for you very quickly. So the conclusion is saying that gamma is virtually something. Gamma prime is a finite index subgroup of gamma. And here, let's look at this first short exact sequence. Here, this is saying that gamma prime is an extension by ZD of some other group, call it delta. And delta itself is a finite extension of some pi1 n prime. And since n prime is a finite sheeted covering of n, this pi1 n prime is a finite index subgroup of that. So the thing we started with is this product here, pi1 of n times zd, which itself is trivially satisfying these two short exact sequences where f is the trivial group and n prime is replaced with n. So the fundamental group of a single piece trivially admits this extension structure. And then the point is that if you assume gamma, if you only assume that it's quasi-isometric to it, we get that algebraically it's like that as well. You may ask, can this be improved to say that in fact, this short exact sequence splits? And sadly, the answer is no. So this is somehow the extent to which you could say that the group gamma is algebraically like this product. Okay. So I think I won't spend too much time talking about this theorem today. Instead, I want to give you more of the main ideas that go into proving this theorem. All right. So, okay. A common technique that's used to prove QI rigidity when you're dealing with manifolds is, well, okay, if you have some group that's quasi-isometric to the fundamental group, what you get is you're going to get a quasi-action on the universal cover of that manifold. If you don't know what a quasi-action is, think it's like an action by quasi-isometries. Technically, that's not correct, but that's the idea. And so often to prove QI rigidity, it reduces to understanding how quasi-isometries of your fundamental group behave. So to that end, we realize that what we need to do at this point is we need to understand the universal cover of this high-dimensional graph manifold. And let me start by describing the universal cover of a single piece. So here's a nice picture that I stole from the internet. So here on the right-hand side is supposed to be the base of one such piece. It's supposed to be a finite volume non-compact hyperbolic manifold. And we have this cusp here. And this loop where we make the truncation, it lifts to these horospheres in the universal cover. That's why I called this a horospherical neighborhood earlier. And yeah, so after you remove this cusp, you pass to the universal cover, and what we get is sometimes called neutered space, sometimes called truncated hyperbolic space. It's the space you get after removing this collection of open disjoint horoballs. So the actual space that this picture consists of is everything inside here. Okay. And now remember that our pieces are this kind of thing times a torus. So in the universal cover of a single piece is going to be this picture here on the left, this metered space times r to the n minus n. Okay. This is the universal cover of a single piece. And now remember, in our whole graph manifold, these pieces are glued along the boundary tori. So when we look at the universal cover of the whole space, universal cover of M, we have what's going to be like a tree of these metered spaces. So for example, let's say one of those boundary tori in the first piece, let's say this is one of the lifts. Again, I'm not drawing the product with the Euclidean factor because that'd be too hard to draw. So just imagine it's always there. And that's, say, maybe going to be connected to this coming from another piece. So you have all these connections. So maybe I'll just draw some arrows. And we're in the universal cover, so you're going to have all these arranged in a tree-like way. Okay, so on and so forth. So what we get is the universal cover of M, the graph manifold, as a tree of spaces. And we have that our group gamma, by assumption, admits some quasi-action on this space. So we want to understand the quasi-isometries of this space. And in fact, what we really want is we want to show that, okay, so as I was saying, I mean, this picture here, this universal cover is admitting some structure as a tree of spaces. You can imagine that each copy of the metered space here is like a vertex, and then you have edges according to where these arrows are drawn. And what we want is we want the group gamma to actually just act on this tree. And then if the action is nice under some Isle conditions, we get to use a fundamental result from Basser theory to conclude what is the algebraic structure of the vertex groups and the edge groups. Those will be the stabilizers of vertices and edges in the tree. In order to show, so the goal now is to show that the group gamma acts on this tree, this underlying tree structure. In order to show that, we would need to show that each of these horospheres gets mapped again to another horosphere up to some finite error. So we want to show that these horospheres get mapped to up to some finite Hausdorff distance from another horosphere. And the tool that these guys use, Frigerio-Lafont-Sisto, used is the asymptotic cone. Now, the asymptotic cone is a really technical kind of construction, so I definitely won't talk about the definition of this. But the way you want to think about it is it's a space you get by viewing your metric space from infinitely far away. So here are some examples. The cone of z squared is r squared. If you have a delta hyperbolic space, its cone is going to be an R tree. And then this third example, which is most relevant to us today, is that if X is what's called a relatively hyperbolic space, then the asymptotic cone is what's called a tree-graded space. Okay, so I will say a little bit more about what this means. The facts about these asymptotic cones that are relevant to us is that they preserve products, which is good because we're going to be taking asymptotic cones of products. And quasi-isometry is induced by Lipschitz homeomorphisms on the cones. So remember, we wanted to understand the quasi-isometries of this universal cover, which is a tree of spaces. And the second fact that I just told you says it's enough to understand the by Lipschitz homeomorphisms of the asymptotic cone. Okay, so given time, I don't have enough time to tell you about the asymptotic cone of the universal cover of M, but let's see how I should use my time. Okay, so here's another nice picture that I stole from the internet. It's called the tree of flats. And what I want to say is that I was first going to try to describe to you the asymptotic cone of a single piece, this neutered space times Euclidean factor. And it's something like this, except, okay, normally in the tree of flats, you have this branching occurring at every integer lattice point. But now instead, suppose that you have this kind of branching at every real point. Here, this is a copy of R2, right? So at every real point, suppose you have this branching, and suppose that occurs on all of these planes. And then what you do is you actually collapse all of the edges between the planes to a single point. So what you get is a pretty wild space. It's totally, it's not locally compact, and the local geometry is pretty wild. But this is kind of the idea of what the asymptotic cone of a single piece is going to look like. And then the asymptotic cone of the whole universal cover is going to be something like a tree-like space obtained from each of these things that I'm very briefly described to you just now. You'll notice that here we have some flats, and that's indeed the case in my situation as well, or the author's situation as well. And essentially what they do is they show that these flats get sent to flats. So on the level of the asymptotic cone, they show that any by Lipschitz embedding of Euclidean space, the image has to be equal to, okay, I didn't see what a wall is, just replace the word wall with a flat. And then when you go back down to the universal cover, that implies that the quasi-isometry you're studying is sending, okay, I wrote in quotes flats to flats because something I forgot to mention. If you're familiar with hyperbolic geometry, each of these horospheres actually under the hyperbolic metric are Euclidean. So they are truly flat. And that's exactly what we wanted. We wanted quasi-isometries to send flats essentially to flats. And therefore we get that the group acts on this tree, this underlying tree. And then by Basser theory and some more argument, you finally get this theorem. So that's the main broad idea, and I should stop there. Thank you.
Thank you, Josiah. Any questions to Josiah? I missed most of your talk because of my internet, so I have
No problem.
like.
Oh. Yeah, it's okay.
Okay. If there is no questions, thanks to Josiah one more time. Thank you, Josiah.